And for problem 2, it needs us to find out that every function can whether cannot be the autocorrelation and or the spectral density function. And for the function A, which is equal to this one, it may represent both of them because we can say if R tau is an autocorrelation function of a real WSS statistic process Xt, then it is even and the R tau is more than R0 and its Fourier transform is non-negative. If S omega is a power spectrum of WSS process, it is non-negative. It should be non-negative. And for this requirement, we can find that the E power by the absolute value of V minus is even, and it is smaller than E power of 0. So it is and also it is non-negative, so it can represent the autocorrelation. Because it is non-negative, it is also a power spectrum. And for the function B, which equals to the sine V squared divided by V squared, it can also represent both of the function because this sine squared tau divided by tau square is even. It's an even function. We can definitely know that. And also, we know when tau goes to 0, the limit equals to 1, and this sine tau is always bigger than tau, which make it non-negative. So it can be the autocorrelation, and also because it is non-negative, it can also be the power spectrum. And for the third function, f equals to 1 when the absolute value of v is smaller than alpha, and equals to 0 when absolute value of v is bigger than alpha. It can't represent autocorrelation because the Fourier transform of this function is to multiple sine alpha omega divided by omega, which is not non-negative. It is not non-negative, and also it is not negative. It can be smaller than 0, so it can't be the autocorrelation. But it may represent the power spectrum because the f omega of this function is bigger or equal to 0, so it can be a power spectrum. That's all.